Hello students, welcome back to the next session on operating system. Today we are going to start with the next unit, unit 4. So under this unit we are going to have two sections. First section is on the main memory management and second section is on the secondary storage management, that is your disk, hard disk and the other devices that are secondary storage. So first we are going to start with the memory management, that is the main memory. So before I start with the theory, now you all have learnt your system, that is the hardware. You have understood that there is a CPU, then then there is an denoted as PC. Then we have, okay. So all this is your CPU, your processor, okay. Then this RAM is random access memory. Now random access memory is nothing but an array of bytes or words. Why we call it as array of bytes or words? Memory accessing, how the memory access is done. Your system is having certain accessing capability, the number of bytes or bits in one set, in one access, how many bits it can retrieve from this memory is called as the size of that instruction. So if your CPU is, you'll have commonly heard 4 byte, your system is a word, 4 bits, 4 bytes is equals to 1 word. Your system will be of 4 bytes word or something like that, right? So you can say 32-bit configuration, 60-bit, 64-bit configuration is commonly known to you all. Your system is either 32-bit configuration or 64-bit configuration. What do you mean by 32-bit configuration and 64-bit configuration? It means that your processor is having a capability of processing that many bits at a time. 64 bits or 32 bits, it can process that many bits. So it can take that instruction, whatever has executed by the CPU with the help of the program counter, is the next address, next instruction location, pick that instruction, get it to the CPU, process it with the CPU, and that is how the CPU or the system works. Now, when you have an instruction, the instruction is put into the CPU and it is executed. This instruction, supposing if this is symbolic representation of your instruction, but in your RAM, it will not be symbolic representation. It will be ones and zeros. So the entire instructions will be in ones and zeros. So the sum is a memory location and equals to is stored in this memory location. Then A is another memory location wherein you have certain value, and addition is the operation that the CPU has to perform, and B is another memory location. So what happens is, supposing if this part of the RAM is given to this program and this instruction is stored somewhere here, it is sum is equal to A plus and is stored here as zeros and ones. What is this? This first variable sum will have this and one. The address of the memory location where that value has to be stored. Okay, so that is sum variable. Similarly, A is another variable, B is another variable, that also has some memory location. So if this memory location is for sum, its address is this value, is this binary number. Similarly for A, you have, this is A and this is supposing B, then sum A and B are three memory locations. In this part of the memory program, whatever memory is allocated to this program, that memory location will have a variable space for storing the value of sum, space for storing the value of A, space for storing the value of B. So this entire thing will make one instruction, but this one converted into 3 or 4 instructions in your machine language. It will say the load A instruction will get this copy of A, the value that is there in A systems in this location. So CPU will execute that load A, then it will fetch this A's value, put it into the first register. Next will be load B and B addition. So it will say load B. So load B will be taken into here. Next is means what? Load the symbol location of A. So here A will not be there. Here the address of A will be there. A's address value into register 1. Load B's this address value into register B. Then sum R1 and R2. Calculate CPU and it will, you will say R1 comma R2. So you will store that. It can be a 3 register instruction or something like that, 2 register instruction. Into your the addition will be saved into your register R3, and then you so what we are saying, the addition of A and B is stored in, then that we are saying store in R from R3, register R3, store it in the location of sum, take it and put it into sum. Got it? So this is how your system works. Now we have the can memory and the main memory. It can your disk. This is your disk. Okay, access the disk because the disk is a memory, it's a device, hardware device, which is access speed is very slow, whereas the next fastest is the RAM. Its next fastest is your RAM. So and then CPU is directly associated with RAM. But because there is these accessing is very fast between the CPU and RAM, the speed of accessing is very fast compared to your RAM. So what we can do is the CPU uses the cache memory. So whatever it is frequently accessing from your RAM, it will be copied here into the cache, and that will be used whenever this registers are full and it needs this accessing of information frequently from your RAM. Instead of going every time to the RAM to access that in your cache memory. So this is the various memories and the various, this is the structure of your system. You'll have already learned this in your first semester or in your BCA. I'm just revising that same because that information and knowledge is required to understand all the algorithms that the CPU, the operating system uses to manage the memory. So it has to manage the secondary storage device, that is your disk, your hard disk, your drives, your pen drives, and all those are called secondary storage. So it will have to access these, it will have to manage these secondary storage devices, it will have to manage the RAM memory, it has to get your program into the RAM and remove the program from the RAM for execution. So if a program has to get executed from the disk, it has to be loaded into the RAM. So when you say play a game, the game will be stored in your hard disk. It will be loaded into the main memory, and then only you can play with the help of your CPU. Similarly, your C program or any of your program, you store it in your hard disk, you bring it into the RAM, and then it gets executed. Similarly, your web pages, they are stored in your hard disk. When you ask for that particular resource, that resource is loaded into the RAM, and then that resource is executed, and then the result of that will be sent to you on the internet. So that is what happens. So your secondary storage device is basically storage device. The name itself says storage. Storage means you want to save them, keep them. Whereas random access memory, RAM, is random access memory. Random access means frequently accessed memory. So the CPU, whatever work, execution it has to do, that program has to be brought into the RAM. And that has to get executed through your cache memory, through your registers, through your program counter, through your index registers, all this. So you have index register, you have base register, you have all those registers that are required to execute a program. So this is what is a background, and now let's understand what is the basics of memory management, and then we will understand what are the different aspects. So what we are going to study in memory management. Under memory management, we are going to study the background, the swapping technique, contiguous memory allocation, then segmentation, paging, and structure of a page table. So what is swapping? See, I told you that from the secondary storage device, you have to get the program into main memory, and from the main memory, you have to remove the program back to the secondary storage devices. This technique is called swapping. Swapping of program from main memory to secondary storage device and secondary storage device back to main memory is called as swapping. Then contiguous memory allocation means you have RAM, and RAM is a contiguous memory allocation. Means what? You cannot put one part of the code here and another part of the code here. You have to have all the program at one place. So that is contiguous memory allocation. How you are going to do contiguous memory allocation? Contiguous means in a streamline. So in one line only, so you are going to keep it all continuously allocated. So that is contiguous memory allocation. We'll see what is contiguous memory allocation, how we are going to do that, what are the algorithms for that, what are the techniques, hardware involved in doing this contiguous memory allocation in that section. Next is segmentation. Segmentation means your entire program will not be brought into the main memory at once. Sometimes you'll see that your take for example any of the applications. Some of the applications will be very large. They will be too large to bring into the memory. More than your RAM may be of 2 GB, but your software may be of 5 GB or something like that. So in that case, you cannot bring the entire program into the main memory. So what you have to do is you have to divide them into segments, which is nothing but like some smaller procedure codes or smaller programs or smaller functions, and execute them. Whenever that particular section of the code is required, you load them into the main memory, execute them, and then remove them when they are not needed. So that is called as segmentation. Next is paging. So entire code is divided into pages, and that we retrieve as a page. So as and how that page is required, we acquire that page from the hard disk. So part of your hard disk will act as a virtual memory. So that is what we will be studying in the next chapter. So the virtual memory is the memory that is extended RAM. So the extended RAM is if the particular program goes for an halt for a particular time, that program is not going to execute. It is on halt position, or maybe it is of a lower priority and a higher priority process has to execute. Then we will remove that program and put it into the virtual memory and get in the program that is of a higher priority or is of an urgent basis. That is executed first. Until then, this process will be kept into the RAM. So that what is kept is what is the paging. So we keep pages into the RAM, virtual memory, and get as and how we require those pages. So all that is what is the main memory management or the memory management, and the structure of the page table is what is very important. So every section of this chapter is really very important. Let's see each one by one. So let's first understand the background of this. What I have explained here is what is here, but it is technical. This is non-technical. It was a simple information of how your main memory works. Now we will understand what are the technicality of this execution. So program must be brought into the main memory, into the memory from the disk. It has to be brought into the memory. So I said from your disk, it has to be loaded into the main memory, and it has to be here for the CPU to access and execute it. Now, main memory and registers are the only storage. Main memory and registers are the only storage that CPU can access directly. Main memory unit only sees a stream of addresses. So main memory is just a stream of addresses that are read plus read request and or add data request and write request. So you can have accessing and retrieving. Like I told you, you can load a value. So from the main memory, you load the value to your registers, and that is used by the CPU for the calculations. And then again, you store it back the value to the main memory. From the registers, you store back to the main memory. You bring the value that is calculated back to the main memory. So I said that your cache memory sits between the CPU and the RAM. So it is what is accessed. So if the information is there in the cache, the CPU accesses it from the cache memory. If it is not present in the cache, then it goes to the RAM, gets it into the cache memory and utilizes it, so that your accessing becomes faster, process execution is faster, and hence it provides you more responsiveness. The user responsiveness, the responsiveness means nothing but how fast you can interact with the program. So that is what is responsiveness. Then you have protection of memory that is required to ensure correct operations. Now I told you that this part of the memory is allocated to a program. Now if the instructions from this the program instructions are in only this part. Whatever data is there, whether it is data or whether it is instructions of this program, are present in this location. So any instruction, if it is trying to access, now I said that sum is an address, A is an address location, B is an address location where the value is stored, right? So this address location, if I'm trying to say, now here you have an instruction, load A into R1. Now by mistake, supposing instead of A's address being part of this memory location, I am taking it as this location. There is 1 bit difference, and hence it has gone to some other memory location. So what happens now? This part of the RAM is not part of this program. Actually, because RAM is divided and the entire RAM is a shareable memory. Multiple processes are kept into the RAM. That's what we saw, CPU scheduling. Multiple processes are there. It picks up the next based on shortest job or priority and executes them, right? So RAM is a shareable memory. So multiple programs will be there in the main memory simultaneously residing. So this program should not accidentally access another memory location, or it should not load its data into this. It should not store the data, executed data, into this memory location, which is part of this program. Actually, it should store only in this much part. But instead of accessing this memory, if it accesses this part of the memory, then it means it is accessing an illegal memory location. It's accessing a wrong memory location. Remember that operating system is loaded in RAM. So the first from 0 to some memory location of the RAM, you will have your operating system. So in this way, if you access your operating system and you rewrite some values, simple, crash, and you will have to reinstall your operating system. Similarly, if this memory location is accessing some other program's memory location, then you can spoil that program. It will affect that program. So that will get crashed. So you will have to re-get the program back to this thing, RAM, and then. So this protection protection has to be taken care by your system. So for this, you have certain hardware that it will be using. We have some resistors that it will be using to check whether the address that I am accessing, the CPU, whenever it is accessing the address, whichever address you have told, it will not access directly. It will first verify whether I am accessing this program's memory location only, or I am using some other program's memory location. So it will check that, and it will take care that this protection is available. It will not harm some other program. It should neither harm the operating system, it should neither harm other programs, instructions, or data. So that protection has to be given. So all this we are going to study in this chapter. So a pair of base and limit resistors define the logical address space. So I told you that this is the location of your program. So what we will do is we'll have this address, the starting address from where it is starting, we will put that into the base register. So the base register will contain the starting location of this program, and you will have a limit register. Whenever the CPU takes this program for execution, first it will load what is the base register and what is the limit register. So this is called as from where it starts, and where it ends is the limit register. So in this example, you can see that the base register, the starting location, the starting address of this process is 3000, some 30040 is the base address, and its limit address is 120900. So this is what it means, that from this location to this location. So if you add that, it will be 4000. The last memory location is 420940. This is the last location that you can access. So if there is any instruction which says access this memory location and get this data or this instruction, then it will first check whether it is within this limit. If it is within this limit, then it will allow you to access that memory location. If it is not within that base limit, if it is not there in that limit, if it is before that, before this base value and after this limit value, then the operating system will create a trap, and it will display an error, runtime error, an execution error. So that is how your operating system is trying to protect. So how this will work: when you are trying to access, the CPU generates an address. That address, it will check with the base register. If it is greater than the base register, greater than or equal to base register, if yes, then it will go and check whether it is below the limit register, base plus limit, whatever is the value, if it is that address location is within that value. If it is yes, then it will allow you to access the memory. Otherwise, it will generate a trap to the operating system monitor and addressing error. It will generate a addressing error. It will raise the error, and it will stop the program execution. So that is how it is taking care of the protection of the program, one program from another program, and program operate from the protection of the operating system also from our user programs. So operating system has an ability to access any memory location because it is managing all the things. It can access all the user programs locations, but one user program cannot access another user programs or the operating system memory. So it has to access only that limit what is allocated to that program. It cannot go beyond that, nor before that, nor after that. It cannot access any memory location. Memory location accessing of other program is only possible when you have inter-process communication. Inter-process communication means two processes are communicating on a shared data. Then that shared data is only the data wherein one program is accessing of another program. So for that also, there is a lot of policies and restrictions of how you can access that memory, and that is what is IPC, inter-process communication. So right now we are not going to in depth of inter-process communication. We are not having we are not going to study in our memory management inter-process communication. We are only going to study how one process can access its own memory. What are the different techniques? How will you manage if the software is larger than your RAM space? Because the RAM space, you have to keep multiple programs in the RAM. You cannot give an entire memory of your RAM to one program. That's why you feel that when you have a smaller RAM, you have and you are using big programs on your system like Visual Studio and all, your system goes slow. Your system reduces its speed because the software is too large to be kept into the main memory, and continuously the software is trying to access a page that is not there in the RAM. It is on a secondary storage device. It has to bring that page or that segment into the main memory and execute that, and again remove that and put. So a lot of swapping is happening, and that context switch is taking a lot of CPU time, and hence your system becomes slow. So that is why we go in for a bigger RAM system. So systems with a larger RAM. Larger RAM, you can give more RAM to such resource consuming big fat applications, and which are requiring less space, that can be utilized with the other remaining space of your RAM. So that's why we go in for a larger RAM systems. Okay, let's understand address binding. So address binding is what? Now I say that your program, raw program, your software is present on your disk. From that it is brought to the main memory, and from main memory it is instruction by instruction is executed by the CPU. One instruction is fetched, it is executed, and then it fetches the next instruction, that is executed, then it executes the next instruction till the entire task is, or the entire program is exhausted. So this program that you have, the program having what is symbolic address? Sum, A, B are symbolic addresses. These are symbolic addresses. When this program is brought into the RAM, you will be having relative addresses. What is relative address? Now this program is loaded at the base address. So if I have sum, so it will be like from base address, this sum, supposing if this location of sum is 32, it is not from the starting location, it's not this 32, but it is 32 from base register. So this is relative address. From base 32. So we are relating it with the base address. So that is why it is called relative addresses. And when you are trying to access it by the CPU, that CPU is trying to access this relative address, but that relative address is converted into an absolute address. What is an absolute address now? The absolute address is where it's actually present at this location. So if this location is whatever is the base plus 32 is its actual location, that is called as the physical location or the physical address, and CPU accesses the logical address. Logical address is nothing but a relative address. Relative address means from base it is at 32 position, at the 32th bit. So 32 bit from base register. So we are saying address is in terms of relation. From the base register, what location it is present. So that is called, that's why it is called as relative address, or it is called as logical address or the virtual address. So this binding of addresses has to be taken. So what is this binding of addresses? Program on disk ready to be brought into the memory to execute from an input queue. So from the disk, the program has to be brought into the main memory, and for this, the programs will be there in the ready queue. So you will double click on any application. That double clicking of that application will cause the program to be brought from the disk to your input queue. From the input queue, it has to be brought into the main memory. So without support must be loaded into the address 00. Actually, all programs have, they think that they will be loaded at the starting address, but starting address is not necessary that you will get the starting address, because operating system will be loaded at the beginning of your RAM. So we cannot load at that address. Whatever address is provided by your operating system for this program, that memory location only you will have to load the program. So it is not necessary that will be in the same location every time. It can be in any location. Wherever that much space that program requires, that much space is available, the operating system provides that space, RAM location to that program. So this allocation of memory also is one of the resource allocation that we saw in the last class. That is what is done by the operating system. So the memory is allocated to your program. So once that is done, inconvenient to have the user process physical address always at 0. That's what I explained you all, that the operating system will be loaded into the, when you start the system only, the operating system will be loaded at location. First program to be loaded in your RAM is operating system. So it will always be loaded at 0, 0. Then after that all your programs will get loaded, and based on what is the memory available, which location is perfect for it, it will provide that memory location. So for the address represented in different ways at different stages of the program's life cycle. Source code, it is symbolic, that's what I told you. A, B, C, all these symbols that we use, name, then class, then division, semester for students. So that is all is symbolic names. So in the program source code it will be symbolic, but when you compile that program, it will generate certain relocatable addresses. What is relocatable addresses? Means the address, we say that its first instruction starts at 0, next instruction starts at 004 after 4 bytes if you are saying. So like that there will be relocatable addresses. This is general addresses which is considering at location 0 our program will be loaded, but actually it will not be loaded at location 0. So that address wherein we are assuming that it will be starting at location 0 is what is relocatable addresses. So that is what relative address or relocatable address, you can say all those words. So 14 byte from the beginning of this module. So that's what I said, 32 bit. Now some is bit from this address. So that is what is relocatable address. So linker or loader will bind relocatable addresses to absolute addresses. Now your loader is a software, system software that will load your program into the main memory. So it is a program that will see, operating system will tell the loader, yes, this program has to be loaded at this memory location. The loader brings that program and puts it into that memory location. So when the loader gets that program and puts it into the location of the main memory, that time the loader will convert the relocatable addresses to actual or physical addresses, which is called as the physical addresses. The linker or loader will bind relocatable addresses to absolute addresses, also called as absolute addresses. So this is the location of an instruction. Supposing if 4000 was its base address, then 14 is its relocatable address. So at 14 that instruction is. So from where? From 74000. So that is the base address. So total altogether will make it a physical address. So 74014 is actual the physical address where the actual instruction or the data is saved on your RAM. So each binding maps one address space to another address space. So compiler, when you compile, that will generate one addresses. Loader will generate another addresses. If you are having linker, it will generate another addresses. Now what is a linker? A linker is a program wherein dynamically you are changing the address. During the program execution is happening. At that time, you feel that one more module of this application is needed. You get that module into the main memory. What location is allocated to that module, that linking happens. So that is all is the different addresses that we see in the system. So binding of instructions and data to memory. So address binding of instruction and data to memory addresses can happen at 3 different stages. So at compile time, load time and execution time. That's what I explained here. When you compile your program, so this is your source code. You have written sum is equal to a plus b in your program. This is compiled. So when it is compiled, you will say 32 is equals to 15 plus 14. So at location 15, there is A's value. At location of 14, there is B's value. Add those two and save it in the location of 32. That is what is the compiler generates this instruction, the machine level language. Then the load time, the loader loads the program into the memory. At that time, this will get changed. If this is loaded at a base of 3, loaded, this program is loaded at that. So that will get added here. So the sum will have address. Sum's address was 32. Now it will get added with the base. that is actual address of your sum in your main memory. So that is load time. So that loading time also the binding happens. Next one is execution time. Execution time is binding delayed until runtime if the process can be moved during its execution from one memory location, one memory segment to another segment. So now what happens? I told you that this program was executing. This is of a lower priority and higher priority process comes. We will remove this from the main memory and put that higher priority process which has to get executed first, and hence this program, when it is removed, it is not necessary it will come back in the same memory location. It can come back in some other memory location. Are you understanding? If this program that is there on the other location, if it finishes the execution, that becomes empty. That memory location becomes vacant. So operating system will bring this suspended process into that memory location. So initially it was here, but later it can be put in some other memory location. So in that case, you all will have to do a dynamic linking of your data. So all your data and instructions have to change their data accordingly. Okay, so that is execution time linking or binding. For this, you need hardware support for address maps like base registers and limit registers. We will be using the base register and limit registers to do all these changes. So these are the multiple steps. Whatever we have explained now, it's the same in the so source program is there, that is compiled or assembled. So you have the compile time, and then it is created as a module, object module. That object module is given as to the linkage editor. The linkage editor will bring all the they include the text in your C program that you write. That is linked into your program. Dynamically loaded. Dynamically, whenever the word dynamically comes, it means that during execution time or during runtime, particular system libraries are brought into the main memory as and how required, not necessarily always. This what this is. Then you have execution time, runtime, wherein this. So now if you remember, we write C programs like hash include, and then we write main. Now what is this? This is your library file, right? And this library file, this is a method, right? If you all know, it is a standard function. It's a standard printf function that we use to display content on your screen. So now this function, where is the definition of this function? This function definition is present in stdio.h. So when you compile this program, so this is a C program, high level language program, you need to compile it. So that's what is compile time. So you all will compile that program and you all will get the object module. Object module is that you in this program you all will have entire print and allow the object module is created. Okay, so that is what is object. Other object modules are added. So this method, whatever code is there, it will be added. Then we have the load method. The load method will only load the main program. It will not load the entire thing. This other code that is required will be loaded at linking time. So when you are calling the printf, that time only the printf method will be called from the stdio.h. So that time only it will be loaded. So that is what is happening at this point. So dynamically it is getting linked. So there are some code. If you load all of this, all the includes that you all have, if you load, For example, nowadays you are having all application development using APIs. You all will have ready-made APIs. You all will just include those API libraries, and you all will be using those APIs for sending email and all that. So if you all include all that into your executable file, the executable file will be too big and unnecessarily takes memory space. If you keep it into the, then you'll have to divide it into the thing. So if you're hardly using those APIs, then it is no use of loading all those APIs into the main memory and loading the main memory unnecessarily with high amount of data. So what we can do is, we can only load the main program, and as and how we want dynamically. At runtime, when I want printf statement, I will load printf. When I want scanf statement, I will load scanf into the main memory. So that library module can be loaded at dynamic time. Okay, so at static time, if it is loading, means before the program is loaded, here it is getting loaded into the RAM. Before it is getting loaded, before the program is loaded into RAM, if your modules are added, then it is static binding. But if you all are, that means the program is binded with your libraries at compile time. So after compilation only, before the program gets loaded into the RAM, the whatever library modules are required, it is added to your first program. But not always all the applications, all the softwares will put or include this libraries into your program, into your executable files, because it will make the executable file unnecessarily big and it will reduce the performance of the system. So what they will do is, they will only keep the main program or the main software or the user program, they will load it on the RAM, and as and how they want the libraries, they will add them during runtime. So that is what is happening at here. So runtime loading happens for dynamically loadable system libraries, and other modules can be added linked during execution. So logical versus physical address space. So we have already understood this. Let's go through that. So the concept of logical address space that is bound to a separate physical address space is central proper memory management. So to do this, we have a system called as memory management unit. We have a hardware which takes care of binding of physical address to logical address, or logical address to physical address. So logical address is what the CPU sees. So it is always referred to as a virtual address, and physical address is what is there on your RAM. So where that instruction is present in the RAM, that is called as a physical address, whereas the logical address is only a relative address. It is there at location 32, means it's not at 32 in your RAM, but it is from the base register 32. Okay, so that is what is physical address. So logical and physical addresses are the same in compile time and load time. So logical address is same at compile time and load time. Address binding schemes, logical or virtual address and physical address differ in execution. Why? Because during execution, the program is in your RAM, and RAM will have a different memory location as compared to your logical address. Logical address is always something like 32, 64, okay. So these are logical addresses. What is a physical address? When you bind with the base physical address. So logical address space is the set of all logical addresses generated by the program, and physical address space is all the physical addresses generated by the program but in RAM. That is logical, which is not in RAM. So we use a memory management unit to take care of this addressing physical address and logical address mapping. So logical address and physical address mapping is done using a unit called as memory management unit. So that's a hardware device that it runs, does the mapping of virtual address space and the physical address space. The simple scheme where the value of the relocation address is added to your every address generated by a user process at the time of it is sent to memory. So base register, now called as relocation register. It is now called as, the base register is called as relocation register, and MS-DOS on Intel 8086 used 4 relocation addresses. So it uses 4 relocation addresses for different programs. The user program deals with logical address. It never sees the real physical address. Execution time binding occurs when reference is made to location in memory. So logical address bounded to physical addresses. How we do that? We have a diagram for that. Let's see that diagram and understand that. So here the CPU generates a logical address. So it says I want to access the A, variable A. So A is at 346. 346 from where? From the beginning of the program. So for the CPU, for your program, it is always 0th location it will start. So 0 from 0, 364th location. 364th bit is the A's starting address. So you go there, fetch A's value. Okay. So, but actually in the RAM, the variable is not at 346. It is at some other location. So for that, the memory management unit will add the relocation address. So if you see, the relocation register is 14000. So that will be added to your logical address and it will generate your physical address, actual address, and go to that memory location, fetch the data and get it to CPU for your execution. So routine is not loaded until it is called. So if you have a particular program, small method function which has all the functions in your program are not loaded at once. Part by part it is loaded so that you can execute only that part which is required around. So all routines are not loaded at once. They are loaded one by one as and how dynamically they are requested for. So when it is needed, that particular method or that particular segment is loaded. So better memory space utilization is possible because of this, and unused routines will be never loaded into the RAM. So that memory space wastage will not happen, because if that routine is not utilized, what is the point in loading them? Then all routines kept on disk is in relocatable load format. With all the addresses, all the instructions are all loaded as relocatable addresses. They are not done, physical addressing is not done on your RAM. In your RAM also you have your variables and your thing will all have, all your instructions will have relocatable addresses only. Only the memory management unit will convert this to relocatable addresses to physical addresses. So useful when large amount of code are need to be handled in frequently occurring cases will be there. So no special support for operating system is required. The operating system doesn't have to bother anything, because memory management unit hardware will take care of this converting logical address to physical addresses. So implemented through program design, and OS can help by providing libraries to implement dynamic loading. So this is how it is easily managing the memory from logical address spaces to physical address spaces. Next is dynamic linking. So here you have two types of dynamic linking. One is static linking and one is dynamic linking. So what is static linking? During the program, when you I told you that you have a program and you have this hash include is added to your program in C program. It is done during static binding only. Static binding. What do you mean by static binding? You'll write a C program. You'll write a hello world program. You'll write and see the number of lines of code. If you see, when you save, it will show you that there are lines of code less. When you compile the program, you see that the lines of code are 300, 400 or something more. Why? Because whatever is part of studio.h, this file lines are also added to this program, this file. So instead of hash include, this hash include studio.h will be replaced with the entire code of studio.h. That entire file content will be dumped in this file. So the number of lines of instructions will increase when you compile the program. So that is what is static linking. Static linking means system libraries and program code combined by the loader into the binary program image. So this entire source code is converted into a object code, and that object code will have studio.h files instructions first and then your main method. Correct? So this all instructions from where they came? They came from studio.h. And who brought them into this program? They are brought by your loader. The loader, when you compile, the compiler will add this files, that file to this file. Okay? So dynamic linking, on the other hand, it is linking during execution time. So the linking happens, whichever library is required at that time only from the linker we get that. So printf uses some method of your operating system to send data to your screen. So that module is not loaded until unless it is not required. It is loaded only when it is required. So operating system modules will be executed by operating system. So that will be loaded at dynamic time. So whatever you are doing with the system, those system operations will require system calls to be made, and system call will wake up some module of your operating system to be executed. So that is what is dynamic loading. So dynamic linking takes place that time. So small piece of code, a stub is used to locate the appropriate program code. So let me supposing now you have space. This is your RAM, and this is a program. In this program space part, for example, to a stub. The stub is a code where it tells where this dynamic linking modules are present. Okay, so either the module is present here or they are present in your hard disk. Okay, so this program instructions are here, all your program instructions are here. This program instruction, supposing if this program instruction requires a dynamically loaded a module, this module is present in your hard disk. So what happens is the operating system will, the CPU will, when it says yes, this has to be executed, the operating system, this stub will have an information of where that routine is present, where it resides, either in the main memory or in your secondary storage device. So it will transfer the control to this memory location. CPU starts executing this part of the code, and if it is not present in the main memory, it will be present in the secondary storage device. It has to be loaded into the main memory, and then the CPU starts executing that module. That module information will be there in this stub. The stub is a small piece of code used to locate the appropriate memory resident library routine. So memory resident means it can be in the main memory or it can be in a storage device. So that will be. So operating system checks if the routine is in processor's memory address. So if it is present in the processor's memory address, this is your memory address. This process P is loaded in this memory. So this is called as a process memory address. So if it is present in that memory address, it will directly start executing. If it is not present, it dynamically links. Dynamic link is particularly useful for libraries, systems also known as shared libraries. So if you have shared libraries and all, it will be very useful and considered applicable to patching system libraries. Versioning may be needed. So you can have versions. So if there are shared libraries like writing the data to your screen, it's a shared library. All processors will be using that when they want to send data to your screen. So that module is shared library. So dynamically linked. When this program requires that module, it will load it. If it is not required, it will remove it. So in that way, it will go on executing it will do the dynamic linking. Next is swapping. Swapping is a technique. I told you that this program is executing right now in memory. Another program with higher priority requires to execute and the entire memory is full. Then no space. This is of a lower priority. It will remove it and put this new process that is required into the RAM. So that is swapping. A process can be swapped temporarily. So it is removed temporarily from the main memory and put it to your secondary storage device. So temporarily out of memory. To a backing store. So your backing store is your virtual memory on your hard disk. Okay. So to a backing store and then brought back into the memory for continued execution. So you can bring back into the main memory when you want to execute it further, when you want to finish its execution. So total physical memory space of a process can exceed the physical memory. I told you your programs can be larger than the memory, main memory. So if your main memory of 2 GB is of 2 GB, your operating system can be of 5 to 10 GB. So what is happening? The entire operating system is not loading in your memory at a time. Only part of that, the modules that are required from your operating system at that time for the system's proper functioning, only those modules are loaded. So when that is not needed, it will be removed. The other one which is not needed will be loaded. So this is swapping. So swapping happens. So that is what is swapping. So you have a backing store, then you have to roll out and roll in of the processes, and you have to have a ready queue for maintaining all this. So we will see all this in the next class. Thank you.